In Chapter 21, we'll examine the difference in reactivity between aldehydes and ketones. We'll look at a series of additional nucleophilic addition reactions that they do. In Chapter 20, we looked only at hydride addition and organometallic reactions. So in Chapter 21, we'll look at different types of nucleophiles that will react with aldehydes and ketones. If we want to look at the difference between reactivity of aldehydes and ketones, it really comes back to one of our 5 core ideas, and that is sterics. So with sterics in mind, hopefully you could already look at the two and determine whether aldehydes or ketones ought to be more reactive. In aldehydes, we have one R group and one H, while in ketones we have 2 R groups. So an R group at minimal is going to be a CH3, which is already much larger than a hydrogen. Of course, both aldehydes and ketones are reasonably reactive due to the sp2 hybrid orbitals on the carbon. So the shape of them is going to be trigonal planar at the carbonyl-carbon atom, which means that something can attack from the top or from the back pretty easily since they're going to be flat. And of course, the other piece to recall is that there's a delta minus on the oxygen and a delta plus on the carbonyl-carbon. So the carbonyl-carbon is going to be a good electrophile, and that's where our nucleophiles are going to attack, always pushing electrons out onto the oxygen. Naming of aldehydes and ketones is something that's probably pretty easy just to read about, so I'm not going to go into that. So I'm actually going to jump ahead now to section 21.6 and remind us of ways to prepare aldehydes and ketones that we already know from previous chapters. So first, let's talk about how to make aldehydes. If we have a primary alcohol and we react that with PCC, pyridinium chlorochromate, then we can oxidize that alcohol up to the aldehyde. Remember, pyridinium chlorochromate is less reactive. If we did this with chromic acid, it would oxidize all the way up to the carboxylic acid. And in this case, we're wanting to stop at the aldehyde, so that's not what we want. From last chapter, we learned that if we have an ester or an acyl halide, that we can reduce that with diisobutyl aluminum hydride, and that reaction will stop at the aldehyde. And again, remember, if we used a stronger reducing agent, something like lithium aluminum hydride, that will reduce all the way down to the alcohol. Another reaction that we learned quite a long time ago is that if we do hydroboration oxidation, react first with borane, followed by hydrogen peroxide and hydroxide, that gives us the anti-Markovnikov alcohol. In this case would be an enol, which will not stay an enol, but will tautomerize to give the aldehyde. Now we've also learned several methods to make ketones already. So another similar one is that we could react a secondary alcohol with PCC again if we wanted to, or with chromic acid, and that will oxidize up to the ketone. We could use a Gilman reagent to react with an acid halide, so in this case I use diethyl lithium cuprate to react with our acid halide, and remember this will add only once, and so when our alkyl group adds only once, we'll stop, add a new ketone. We could also do Friel-Crafts acylation, starting with the acyl halide and aluminum chloride. That will add the acyl group to our aromatic ring, again forming a ketone. And we can also return to the alkyne reaction this time if we react with acid and water. Now instead of getting the anti-Markovnikov alcohol, we would get the Markovnikov alcohol, which again is an enol. Since it's an enol, it will tautomerize, in this case to form the ketone. Another way that we can make aldehydes or ketones is to do ozonolysis, so ozone with zinc and water. And remember, with ozonolysis, we'll cleave this bond in half, and both sides will be oxidized up to a carbonyl. So if I look at my product here, the top one, because it was di-substituted, ends up being a ketone, while the bottom half of the alkene is monosubstituted, and that one ends up being an aldehyde. So ozonolysis can form aldehydes and or ketones depending on the starting material structure that we react with.